Okay, so I'm going to do this section a little differently this year. I'm going to first off start you off with graphing, writing an equation from the graph of a rational function, and then we'll reverse it, and I'll give you the function. And you're going to have to graph it. So, but for Monday, you want to be able to do this. So before we get there, I want you to call your attention to a couple of toolkit functions we looked at way back at the beginning of the year. And one of them was the reciprocal function. Okay, and that looks something like that. The function was y equals 1 over x. And some things to keep in mind about this: as x approaches negative infinity, we can see that y heads out, approaches 0. And as x approaches positive infinity, this y value gets lower and lower and lower until y approaches 0. And when you did that work earlier, you noticed that the domain doesn't include 0 because I can't divide by 0, and the range won't include 0 because 1 will never be equal to 0. So, because 0 divided by a number is 0. And if I can never get the numerator of a rational function be equal to 0, there's going to be no x-intercepts. So let's finish off this arrow notation. So as x approaches positive infinity, y also approaches 0. So that's some things to keep in mind. And so a couple of pieces we want to think about. There's a vertical asymptote, that should be a v, a vertical asymptote wherever the denominator equals 0. So in this case, when x equals 0, there's a vertical asymptote at x equals 0. And 0 is not included in the domain. The other thing that happens with this is there's a horizontal asymptote. And we're describing what's happening out here at infinity. So if you think about these the ending behavior of these rational functions, they both approach 0. So the horizontal asymptote is the line y equals 0. And we're going to learn some tricks. We're going to learn some tricks about this as we go. The other toolkit function that I'm going to call your attention to is here. Let me add a page here. So the other toolkit function is the reciprocal function, the reciprocal squared function. And what happens with those, as you noticed when you did that material, it looks like this. So basically, if you think about it, remember how the reciprocal function had that piece down here, and then it had this piece up here? Well, if you square it, it's going to act just like over here. So if x equals positive 1, it's going to act the same as y equals 1. So thinking about this is an even function because f of negative x is the same as f of x. So something to keep in mind with that. Basically, in the short run, what we can think about is x approaches that vertical asymptote, it's going to head in the same direction. And as we head out to infinity, again, x is going to get very large. So as x approaches negative infinity, y is going to approach 0, and as x approaches, I'll write it over here, as x approaches positive infinity, y also approaches 0. Here, let's put an arrow so we know it approaches 0. It's not equal to 0. And again, the domain doesn't include 0. The numerator will never be equal to 0, so there's no horizontal intercepts or solutions, right? So those are the two toolkit functions, and now we're going to talk about the variations of this. So the first problem I grabbed, and this is one of the even exercises out of this section in the textbook. Well, there's a couple of things happening here. You see how I noticed there's a vertical asymptote here and there's a vertical asymptote here, and they were nice in the textbooks. They gave us the lines. So I know those vertical asymptotes have to occur in the denominator because I can't divide by 0, and that's why those vertical asymptotes occur. So if x equals negative 3 and x equals positive 4, I can treat those as factors by just moving those values to the other side, and that gives me my vertical asymptotes. They go in the denominator, I can't divide by 0. And then I'm noticing this graph crosses the x-axis at x equals 3. And that's the only 0. So what I can think about is, well, when x equals 3, the numerator is equal to 0, so I know that goes on top of the rational function in the numerator. And then the only other thing we got to worry about is this y-intercept here. If I substitute in 0, do I get negative 2? Well, that will give me negative 3 over positive 3. Those cancel out. And over negative 4, so I'll get 1 over negative 4, which is not negative 2. So there must be some stretch factor going on here that we have to find. One other thing I just realized I didn't talk about, this function here is acting like 1 over x. Remember how 1 over x acted like this? This just so happens that it's been reflected around the x-axis, and it's acting, if you just look at this piece of it, you see how that's acting like 1 over x, but it's just been reflected on the x-axis. We'll take care of that when we're finding the a. And the same thing here, at x equals 4, it's acting like 1 over x. It's just some kind of reflection going on. So we know probably a is going to be a negative number, but we won't include that yet. So we're going to look at that point 0, negative 2, and I'm just going to replace every place I see a y, I'm going to write negative 2. Every place I see an x, I'm going to substitute in a 0, and I'm not going to bother writing 0 minus 3. And that's going to be 3 over negative 4. And if we do some arithmetic here, we get negative 2 equals, let's see, the 3's cancel, the negatives cancel, so that leaves me a over 4. And isn't this just a proportion? So if I do the cross products, a will equal negative 8. So that tells me right here, I should put, I don't know if I can erase that a, it's not going to let me. So I'm just going to write a negative 8 here, and that is a rational function that will represent this graph. So we looked at the vertical asymptotes, we looked at the 0, we looked for a stretch factor. Oh, we also looked whether it acts like 1 over x or 1 over x squared. So here's another rational function from that section from your textbook. And so the first thing I'm going to look at is I'm going to look for my vertical asymptotes. So this has a vertical asymptote at x equals negative 3. This has a vertical asymptote at x equals 4, but I want to call your attention to this. This is acting like 1 over x. This one over here is acting like 1 over x squared. They're headed into the same direction. Granted, it's been reflected around the x-axis, and we'll take care of that as we start finding some other values. But to start off, I'm going to write my rational function. I'm going to write x plus 3. Remember, we're changing the sign. Remember, that's x plus 3 to get the factor. And this other one becomes x minus 4 to get the factor. So we want to remember, we want to know when did these things equal 0. And then since this vertical asymptote here is that the function's acting like 1 over x squared, we're going to square that vertical asymptote, and that will force the graph to head down like this in the same direction around x equals 4. And then I'm noticing it crosses the x-axis at x equals 2, so I'm going to write x minus 2. I know that gives me a 0. And then I've got to ask myself, if I substitute in 0, do I get positive 1 in that equation? Well, I'm hoping you see that no. So what I'm going to do is I'm going to say 1 equals a times, well, let's see, that's going to become 0, that's going to become 0, that's going to become 0. So I'm going to get 1 equals a times negative 2 over 3 times 16. Remember, we're squaring the negative 4. And then we probably should simplify, reduce that fraction a little bit to make it a little easier. So 2 and 16 simplify to 1/8, so I'll get a negative 1a over 8 times 3, which is 24. And then if I just treat this like a proportion, I can do the cross products. I'm going to find out that a equals negative 24. So what I'll have to write here is negative 24. So I thought I'd write that all as one final answer so you could get that down. Okay, important part that people always miss is thinking about this as 1 over x squared. You got to remember to square that. The other piece that people mess up on is your zeros. Remember, there's zeros where it crosses the x-axis have to go on the top. And also check for that stretch factor. So for this one, I am seeing what? I'm seeing a single vertical asymptote at x equals -2. And I'm also seeing that it acts like 1 over x, so I don't have to square it. I'm seeing a single zero at x equals 1, right? So I'm going to write x minus 1. And, oh, and actually, I'm sorry, there's not a single zero. There's another one over here. So x plus 4. And then I'm going to ask myself, if I substitute in 0, do I get positive 1? Because that y-intercept is 0, 1. Well, let's see. 1 times, oh, that's going to be what? That's going to be -1 times 4. Right, -1 times 4 is -4 divided by positive 2 is -2, not positive 1. So there is some kind of stretch factor going on. So a times -1 times positive 4 all over 2. So 1 equals, let's see, 2 goes into 4 twice. 2 times -1 is -2 times a. So I'm going to divide by -2. So a equals -1 over 2. So then what I can do is I can just do -1 over 2. And that rational function will make it work. You can also write -1/2 out in front, and this works with any stretch factor. X minus 1, x plus 4 over x plus 2. Before we leave this question too, I'm not going to ask you to do much with this right now, but this is to prime you for next week when we start looking at equations and graphing the equations. If you were to expand this all out, wouldn't you get an x squared? And that's just over an x. So this is what's called a top-heavy function, because the degree of the numerator is larger than the degree of the denominator. And notice, I'm not getting a horizontal asymptote. I'm getting a slant asymptote. So part of that's one thing we're going to explore next week is what's up with that. Okay, one thing I should have added to your paper before I printed them was this y-intercept. We're going to call that 0, 1/4. So why don't you stop this video, try to do this problem yourself, and see if you can't get an answer. Come close. I'm going to point you out to a couple of things. This acts like something special is happening here. Something not so special is happening here, but it's still important to note. And what's happening here at this 0? It looks like to me it's coming down and bouncing off the x-axis. So think about when we were working with polynomials, how we dealt with that. So anyways, yeah, stop this video, try it, come back and watch what I did. So I'm seeing a couple things here. I hope you tried this by yourself. I'm seeing a vertical asymptote at x equals -2. It's acting like 1 over x. So I'm just going to write x plus 2 and close it in parentheses. This vertical asymptote is acting like 1 over x squared. So I'm just going to write x minus 4, but then I'm going to square it. Then I'm noticing this special 0. It's acting like it's bouncing, which means it should have multiplicity 2. So I'm going to write x minus 2 squared. And then to make sure that I've got the right values here, what if I substitute in 0? What if I look for that y-intercept? Am I going to get 1/4? Well, I'm going to get 4, because I'm substituting in 0, right? Over 2 times 16. Well, 4 goes into 16 8 times. That's going to give me 1 over 16 as a y-intercept, which isn't 1/4. So, I mean, we could think, well, maybe that is 1/16. I don't think so. I think it's up a little too high to make it 1/16. So we'll pretend it's 0 1/4. So in that case, what's going to happen is here. Let me come back and delete some of this if I can. So I know that if y is 1/4, x has to be equal to 0. So that's going to tell me, let's see, remember I'm substituting in 0 here, so negative 2 squared is 4. And there's an a going on here. A times 4. A times 4. And then in the denominator I'm going to get 2. And then negative 4 squared is 16. So 1 over 4 equals, let's see, we're going to do that same simplification I did earlier. That's going to become 4. So it becomes a over 8. So then if we multiply on both sides by 8, or do the cross products, however you want to deal with this, you should find out that a equals 2. So we're going to write 2 times x minus 2 squared over a plus 2 times x plus 2, sorry, x minus 4 squared. That rational function should give us a graph that looks something like this. Okay, so for this one, looks a little different, but not all that different. I'm going to take care of that vertical asymptote at x equals negative 2 by writing it as x plus 2. And it's acting like 1 over x, so I don't have to square anything. Same thing happening at x equals 5, so I'm going to write x minus 5, and it's acting like 1 over x, so I don't have to square anything. I'm seeing a 0 at 0, so I could write x plus 0, or let's just write x. And I'm also seeing it crosses the x-axis at 2, so x minus 2. And then this horizontal asymptote is pretty cool, because because I've already dealt with the y-intercept, I really can't use that like I have in the past. So something to keep in mind is if I were to expand both of these, the numerator and the denominator out, my biggest power would be x squared over x squared. And because these are the same power, they basically cancel out. Way out at infinity, all the other terms don't matter, and even this will cancel out. And what I'm seeing, it's got a horizontal asymptote at 2. So if there's a horizontal asymptote, there must be a 2 stuck in front of there. So, and that's what you can just do. If you see the horizontal asymptote, you don't have to worry about solving for a. That is the stretch factor. Okay, as long as it's the same power, as long as your rational numbers or rational expression has the same degree in the numerator as it does in the denominator, if there's a horizontal asymptote, you can stick it in there. If they aren't the same, you're not going to see that. So that's a nice, easy shortcut. So remember, horizontal asymptotes, you just stick it in front of the numerator. You could also put it in front, and that would be okay too. So for this one, again, I just see the horizontal asymptote, so I know there's going to be a same degree in the top, same degree in the bottom. I'm noticing this one's acting like 1 over x squared. I'm noticing this one acts like 1 over x. You see the way this graph crosses that horizontal asymptote? That's okay in the short run, but what we're going to see is what's happening way out at infinity. It'll settle down and become that horizontal asymptote y equals negative 1. Okay, so it's okay for a function to cross a horizontal asymptote where you just worrying about what happens out at infinity. That won't happen for a vertical asymptote, because if it crosses the vertical asymptote, it's not a function. Because it's not defined there. Let's see here. So what I've got to do. So I've got my vertical asymptotes of x plus 3, and that one's acting like 1 over x. I've got a vertical asymptote at x equals 1, and that's acting like 1 over x squared, so I square it. I also see that there's a 0 at x equals 1, so that tells me x equals negative 1, sorry. So that gives me x plus 1. But also you notice the way this one doesn't just bounce, it wiggles through that. So that tells me that has a multiplicity of 3. And then if I were to expand these all out, just to call your attention to this, x cubed on top, x cubed on the bottom, it's going to have a horizontal asymptote. We can just stick that y equals negative 1 in front and be done with it. So remember, that x equals negative 1 is from this horizontal asymptote right here, not that negative 1. Okay, last problem, which should jog your, or call your attention is that hole in this graph. So I'm seeing a vertical asymptote at x equals -1. It's not acting like 1 over x squared, so I can not worry about that. I'm seeing a single 0 at x equals 3. So x plus 3. And let's see, it has a y-intercept of 0, 3. So let's see if I get that if I substitute in 0. If I substitute in 0, do I get 3? And sure enough, I do. That becomes 3 over 1. So I don't have any kind of stretch factor. If you want, you could put a 1 here. Now, the only other thing I haven't dealt with is this hole. Well, if there's a hole, that tells me the function is not defined at x equals 2. So I'm going to have to put x equals -2 in the denominator. And I also know if I just have an x equals -2 in the denominator, this should be a horizontal asymptote. I mean not a horizontal. This should be a vertical asymptote at +2. But we're seeing the hole. So what you have to deal with is put the same term in the numerator. And that way, if you try to substitute a value in for x equals 2, that's going to give you 0 over 0, which doesn't make any sense. And in calculus, it's where we're going to start with. But what that tells us that there's a hole in the graph. There's not a vertical asymptote. Okay, so hopefully that you'll see another one like this in the assignment I'm going to give you, and you'll see something like this in the My Open Math assignments. So that's writing a rational function from a graph. Hope this helps you do it. Let's get to work on Monday.